All right. Let's get started. I should have made that comment about small numbers today instead of on Monday. Even more true. But again, they're all recorded. It's fine. It's okay. So today we're going to be talking about some more P3 BCIs. We're going to focus on a couple of, mostly we're going to focus on spellers, but I will talk about a few that are related to cursor control. And then on Friday, we're going to be talking about linear discriminant analysis, which is the main classification algorithm that people use in these BCIs. Not exclusively, of course, but it is very, very common. And it goes all the way back to the first BCI speller even, which, as a reminder, was Talking Off the Top of Your Head by Farwell and Donchin. And I think this speller and this design of the system says a lot about what the point of a lot of brain-computer interfaces is. So the goal for a lot of these spellers is not to create a paradigm for somebody who is able-bodied and able to communicate through conventional means like speaking or writing to communicate. It's made typically for people who are in something known as a locked-in state or a completely locked-in state. So we'll call them LIS patients or CLIS patients. And they comprise a very small portion of the population. I did the back of the napkin math before my advancement, and it's something like there are an estimated 24,000 people in the entire world that are in a locked-in state. So 24,000 out of 8 billion is pretty small, but they still exist. And I think I did the math, and it was something around, I don't know, there are like in any large city, there are tens of these people. And it just so happened that when Farwell and Donchin were doing some of this stuff, it was part of the DARPA-sponsored biocybernetics program, which was sort of this initiative that lasted through the 70s and 80s of DARPA trying to create things that are going to be, connecting the brain and the mind. So people are making all sorts of different interfaces. This is when BCIs really started taking off, and it was, from what I've heard, it was a very good opportunity to get a lot of funding to do research. And Donchin was particularly well-funded because he was the top P300 researcher at the time. And he was at the University of Chicago, Illinois, Urbana-Champaign. And some person, I can't remember their story, had an accident. They ended up hitting their head and going into a locked-in state. And the person's mother was convinced that they were still conscious, but they were just locked in. And the physician that was treating them was like, oh, I've heard of this DARPA biocybernetics program. So he phoned up DARPA or wrote a letter to DARPA saying, hey, I have this patient. They're completely locked in. Someone logged into my Zoom. You're good, just mute it. So anyway, they were completely locked in. Physician sends a letter to DARPA saying, hey, is there anything you can do? DARPA responds with, and I think this is like an exact quote, but you should go to the psychology building, look for Manny Donchin. We've stuffed his pockets with plenty of money. He should be able to help you. And then he did. So Farwell and Donchin created this speller. They were working on similar stuff because of the funding, but they created the speller for an actual locked-in patient. So that was the original goal, and that still tends to be the main goal for most of these spellers. Now, one thing that you'll notice when reading through the literature is that most of these are tested on healthy undergraduates first, and they tend to have a lot better performance than people who are locked in or completely locked in. So a lot of the things that end up being useful are not just getting higher classification accuracy, for example, but making the actual responses that participants get stronger. So if you have a certain paradigm like this that will get you a P300, and you can see it in locked-in patients, the goal is not necessarily to make that spelling more accurate necessarily or make the classification more accurate just by itself, but in general, your goal is a goal can be to accentuate that P300, get a larger P3B amplitude so that you can see it more readily in a larger set of participants. Now, of course, this is 2023. Machine learning is huge. People love doing that type of research. It's a lot of people's careers. So there are a lot of people that don't design new brain-computer interfaces. All they do is take existing paradigms or take existing data and try to increase classification accuracy. That's definitely one side of brain-computer interface research, but it's not the whole field, and it just, in raw honesty, that doesn't really make that much of a difference to the people who need it. A lot of the best BCIs that actually work for people use very simple classification algorithms like LDA and support vector machines because they work. So a lot of this fancy, let's throw more and more data, more and more deep learning at it, isn't always necessarily a useful thing for the people who are actually theoretically building these tools for. So I'm going to talk about some BCIs that were made with these people in mind and that utilize interesting phenomena to try to increase spelling performance. So this was published in 1988, and according to this paper from a few BCI researchers, from 1988 to 2000, there were no P300 BCI peer-reviewed papers. So there was just sort of this dead zone. And part of this was because the biocybernetics program was winding down. There was this weird phase where neurofeedback got really popular and then didn't actually work, didn't do anything. So all of BCIs and neurofeedback sort of had a bad reputation. It's like, oh, this is a waste of time. Of course, it's still to be determined whether or not that's true in the long run. But starting in 2000 and all the way through now, BCI sort of got a resurgence. And that's not relevant. What people started doing was they started taking the original row, column, matrix, grid speller, whatever you want to call it, and they started making modifications. So one of the things that people tried was to take this parallelized design and instead use a single character approach. So in this case, rather than flashing an entire row and column, you would flash a single character. And although you'd think this would be worse because you're no longer spelling in parallel, you can flash stimuli more rapidly. And even if you do it slower, I think you get a stronger signal. And also during the training phase, you can make it so that no neighboring letters to the target stimulus are illuminated, meaning that you can get a more clear discrimination between when the participant is looking at their relevant target stimulus or not. There's also, if you have this design, you're also technically making the target stimulus more rare, which is good for the P300. So if you illuminate every row and every column, let's say you're going to illuminate all of them in order, then if you have 12 different illuminations, 2 of them are going to contain your target. So the probability is 1 in 6. But if you're just illuminating every individual letter, then and character, then in this case, your target probability is 1 in 36. And the biggest effect on the P300 by far is the probability of the target being low. So the lower that target probability, the better the P3 amplitude is going to be. If you have a scenario where the target is very frequent, you will still get a tiny P300, but the biggest influence is if it's rare. So this single character speller can be technically a little faster, but I think in the end it ends up being less accurate. And in general, it seems that you would get more of an improvement by probing in parallel. So it's somewhat counterintuitive, but this is people starting to think about how can we remix this original design. Another one that was really popular is the checkerboard matrix. So now we have the exact same grid, essentially, but rather than illuminating rows and columns sort of at random, they're illuminated in a sequence. So first you do the white rows, then you do the black rows, and then you would do the white columns and the black columns. And the original checkerboard is actually, I think, like from the actual paper, it's larger than this, but I didn't want to remake my little table. And one of the things that's useful about this is that it it does 2 things. First of all, it makes it so that you can guarantee when what the minimum number of distance is between two targets. Because it's always going in this predictable sequence, you can guarantee that, okay, if my target letter is A, there's never going to be a situation where I flash the row for A, and then immediately I flash the column for A, because remember that that's also bad for the P300. So when you have a target stimulus followed by another target stimulus immediately afterwards, you're going to get a lower P3 amplitude than you would if you had the target, a bunch of non-targets, and then another target. Part of this is temporally related, but it's also dependent on what the previous stimulus was. So in this case, you always have a minimum distance, I think, of 6 stimuli between two target flashes. You also reduce the chance of paying attention to aberrant stimuli. It's not that much of a modification, right? This is still very much the grid that we're familiar with. It's just a subtle manipulation, and it's not particularly innovative. But it's slightly better. The researchers who designed this also tried adding a predictive language model in order to, try to spell words more accurately. I also believe that the letters were shuffled every time, so it wasn't necessarily always in this configuration, but the commands would be moved around randomly. And they also showed that if the participant does some mindfulness, meditation, or training before spelling, that they can increase the accuracy and the speed. And then comes the hexospell. So this was originally a motor imagery BCI, and we'll talk about it when we talk about motor imagery, but in that study, essentially you would have, think of this as like a phone dial, and what people would do is they would think of either rotating left or rotating right, and the dial would, once it's classified, would move in that location. And then once the larger collection of the potential letters is selected, they get expanded out. And they use this exact same design with the P3 speller. Yeah?
So with locked-in patients, if they've been locked in since birth, let's say, do they have the actual connections to be able to move right and move left using motor imagery? Do they still have those?
Good question. So this was about if a person is born locked in at birth, do they have the ability to think, move left or move right? So that's an interesting question. So something like motor imagery is not just useful for locked in, right? It could be useful for somebody who's paralyzed, paraplegic. There are people who are born like that. The brain is very adaptive, and if you are not using certain regions of it because you can't, it'll tend to get hijacked by something more useful. We've seen this a lot of times. So theoretically, if you have no sensory connections to limbs and stuff, you might not have a lot of real estate on the cortex left to think about what it feels like to, move your right hand or move your left hand. And in motor imagery, again, we'll talk about this later, we actually try to have participants do things that are pretty sensorily rich, or try to not just imagine moving your left hand or imagine moving your right hand, but imagine grabbing a very familiar door handle, like the entrance to your childhood home or something, and like the texture of that, imagine turning it. Obviously, we don't have participants actually move their hands. We want to avoid that. So we record their EMG to make sure that they're not actually moving their arms or their hands. So yeah, I think it would be much harder to get this working on somebody who was born in a state where they just didn't move their limbs. But it should, I don't know. Things like this, like if you're designing a BCI for that kind of person, maybe you would try motor imagery first, and then you would end up trying something else like a P300 speller or an SSVEP or something like this. Yeah, very good question. Yeah. Yeah, so I'll focus on so the question was if they're always moving this dial, essentially, how are they focusing on a specific character, or how are they selecting one? So I'll talk about it in the context of the P3 hexospeller, since that's more on topic. But what's happening is the participant in this case is going to be focused on one of these letters. Let's say it's C. And iteratively, each of these circles is going to flash, so they're going to be highlighted essentially. And I don't have all of them illuminated, but it would do this one, then the next 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 one. And what we're looking for is that P3 response, because the circle that contains your target, when it's illuminated, we should see a P300. Once the circle is selected, the remaining circles are removed, and then now we expand the characters into the new grid. And then we'd go through it again and illuminate, C, then D, then E, then A, then B. Does that make sense? So this is, I remember when I asked what are certain improvements that we could make in order to speed up spelling accuracy or speed up speed, increase speed, that I think someone mentioned binary search. So this is very similar to that. It's not exactly binary search, but you're still taking the same methodology of clustering multiple things into smaller categories, and then once you get into that category, you iteratively search within them. So this is good for you could theoretically use this design not just for letters, but for entire commands. So let's say you're trying to control, use this not just to spell, but to control some sort of computer system. In certain cases, you could have this be icons, you could have this be like the browser and word processor and paint or whatever you want. So it's not just limited to characters, obviously. But it's a cool design. And there are other spellers similar to this, not just the hexaspell. One of the authors of the paper that I quoted earlier worked on, or two of the authors worked on one that was similar. But originally, the hexaspell was a motor imagery that was then adapted by the same researchers for the P300. And then we get a very interesting set of design decisions. So we know that this grid speller works, right? But we also know that the stimuli, aka just letters being illuminated, are not necessarily the most emotionally or naturally salient stimuli that humans process, right? We didn't evolve understanding of characters or looking at these. Our brain isn't explicitly designed to respond to these things. So what some researchers did was they said, okay, let's take the grid speller, but rather than illuminating them, let's show faces of famous people instead, because this has a couple of interesting ideas behind it. We know that first of all, we evolved to look at faces and to recognize faces. This is something that is very evolutionarily viable. So we have a lot of real estate in our brain for recognizing faces, whether or not they're faces we are familiar with or not. This also allows us to use not just the P3 complex that we normally get from an oddball paradigm, but we also add new ERP components. So there's one called the N170, and the N170 is very salient to faces. So if you show somebody a face, you'll get a strong N170. If you show someone a familiar face, you'll get an N170 and what's known as the N400 face, or N4F. And if you see your own face, you get the strongest N170, which is something that I'm using for another one of my studies, actually. It's not a BCI, but it is an ERP study. So the goal for this was, okay, let's take a design that we know works, and the only thing we're going to do is we're going to use some famous faces and see if that increases speller accuracy and performance just by the virtue of, hey, our brain is good at looking for and looking at these stimuli particularly. So that works pretty well. And I think they tried a bunch of different types of faces. I think Einstein was one of them, and they used a bunch of other famous people. But it's an interesting thought, right? It's okay, biologically plausible. It's an iterative design. It's based off of a lot of literature. So it's good. And then some researchers took this idea and they wanted to explore it even further. So they not only did they use faces, but they also modified the faces. So they would take a face, they would take that same face and remove the eyes from it, because maybe that has some interesting neurological response, right? The brain is expecting to see a regular face. So you see this eyeless face and maybe you get some additional uncertainty, maybe you get this additional component of surprise, and maybe that makes spelling accuracy better. They also did the opposite, where they just used the eyes, and then they had an object, And they took all of those and they inverted them as well. Because the same reason, right? It might take more processing. It might be a little more confusing. It might be harder to process these inverted faces or these inverted objects. And as long as it's still recognizable and the task is relatively easy, this might not make the accuracy worse, but instead might turn it around and be like, okay, the brain is working harder, it's producing larger potentials or weirder or newer potentials, whatever. And because of that, we can get more discriminable signals between targets and non-targets. And then the default one is just the highlight icon. So in this particular design, this wasn't a speller, but instead cursor control. So that your goal is to look at, you're gonna, in the training scenario, you're gonna get a direction that you're gonna focus on, and you're gonna look at that, and then you're either gonna see a face over that direction, or a car, or eyes, or you're gonna see the regular icon highlighted. So this is a lot of different stimuli to try, and I'm curious on your intuition, what do you guys think would be the worst performing one? So I have two questions. I have best and worst. So we're going to start with worst. All right. We'll give this some time. So yeah, which one do you think is going to be the worst? And I think all of these are labeled correctly. We'll find out when it's done if that's not true. And again, same thing with all of the other ones that have a technically correct answer. They don't have to. Your answers do not have to be right in order for you to get participation. So yeah, just think about it. And if anybody's interested in explaining their reasoning why they think one is going to be worse, I would love to hear it or see it in chat. Is class question working, by the way? I'm not seeing any answers yet, so I just want to make sure. Good? Cool. Yeah, take some time to think about it. Interesting. The UI is glitched. I'm seeing total answer 0, but when I click on the results, I can see that there are 55 responses. Okay. So I'm going to assume that was most people. I'll let it go down to 3, but does anybody want to explain why they think which they chose was going to be the worst? You don't have to, but I like to hear the thought process. Yeah.
I mean, my initial thought was that like the highlighted icon would be the worst, just because the face, even the iris face and the object are things that like we recognize on a day-to-day basis.
Sure.
That would probably be like trained to recognize faster, but an icon doesn't really have a lot of meaning on its own. So
cool. So that's a good hypothesis. So the answer was that, or the answer they gave was, okay, highlighted icon's probably going to be the worst because even though it's not a face, even though the objects aren't a face or anything, they're things that we see all the time. So it's got to be better than this random highlighted icon, which is sort of meaningless outside of the context you're looking at it. That's a good answer. Did anybody choose anything that wasn't I that wants to give their answer a shot? Yeah. Got it. That's interesting. So another student chose H because an inverted object might not necessarily be recognized as the original object. So it's also something that might add confusion, might make the discriminability of the actual stimulus harder, which is interesting. And those hypotheses are correct. So if you have certain stimuli that are not recognizable, like let's say you just took these pixels and you rearranged it, that would be just randomness. You wouldn't be able to recognize anything from that. But I think if you're not randomizing it, maybe there's still a chance of recognizing the object. But let's look at the actual truth. And current question, results. All right, so this is what we got. So most people tended to be on the H train as well. And so the real answer is the highlighted icon. I'll show you graphs of all of them, but this is actually a pretty good spread. So inverted eyeless face was the second most popular. Anyone who chose that, what would you be interested in sharing your reasoning? Just out of curiosity. I mean, it's not a bad guess, right? I mean, this is a weird stimulus. Doesn't make much naturalistic sense. You first and then Cassia, yeah.
For me, I chose this answer just because it's kind of weird. When you look at someone's face, your first impression is to look at
Sure.
their eyes. But in this image, it turns out like you cannot really find eyes on this face.
Got it. Cassia, is yours similar to that?
Very similar. I said you usually recognize people by their eyes, and also the fact that it's upside down means that you probably won't recognize it as a person if it's flashed really fast. So I was like, it's basically a useless picture. So
Got it.
You're not going to form any type of response to it.
Yeah, so the first answer was, when you're looking for a face, you're typically looking for eyes, and if you don't see those, maybe you don't even recognize it as a face. And then similar point where if you don't have those eyes to lock into, maybe your brain doesn't even necessarily process it as a face. An interesting set of ideas, and I get where you're coming from on that. So let's go to the next one. So the next question is exactly the same images still, but now which is the best? So which do you think would perform the best out of all of these? And I'll give that some time as well, and we'll see if my UI is glitched. And again, same thing, open invitation to anyone who wants to talk through their decision for which they think is the best and why. I'd love to hear it. Yeah.
I said A for face.
Okay.
Because that's quite cool for humans, and we see face all the time.
Sure.
We're probably trained to recognize that quickly.
Yeah, that's sound reasoning. So in this case, the student said that A is going to be the best because it's a face. We look at faces all the time. Our brain is super good at looking for faces, so it should be super good at giving us a response when we see this face. Makes sense? Anybody else who's not selecting A? Have a different take? Any wild cards? Yeah.
Maybe the eye more zoomed in.
Sure, yeah. So the student answered I, maybe because it's more zoomed in. So I guess this would be more in the hypothesis that the thing that we're really looking for in these faces are the eyes, something around that. Yeah, that's an interesting guess as well. I'm surprised there's no car lovers that are being like, oh, I definitely would recognize whatever car this is better than I would recognize whoever this is. And it's interesting because in some studies, especially working memory studies, you show that people who are experts in certain domains are equally good and they have a very similar response to seeing objects in a domain they're familiar with as they do with faces. So I'm sure you guys have heard of the fusiform gyrus if you've taken neuroscience classes. And the fusiform gyrus is often called the fusiform face area in the brain, but that's a bit of an oversimplification. It's really good at responding to faces because we see them all the time. We're naturally experts with them. But if you become a car expert or a bird expert or an expert in whatever niche thing you have and you see stimuli in that category, the fusiform gyrus responds almost identically to those objects as well. I'm not saying that this would happen in this case, and I think the participants that were used in this experiment were just everyday people. It wasn't like you're taking non-experts and experts and comparing their responses. But everyone always says the fusiform face area, and it's not technically correct, so figured I'd throw that in there. Okay, let me see if I have a lot of responses. Looks like 57, fewer than the last one, but okay. And I'm going to end the current question. And now let's check the results. This is interesting. So the vast majority of people chose A, which makes sense. But in reality, what the researchers found was that the inverted face was the best one. So similar logic to what you guys were saying and probably what everyone was thinking about when they chose the face, except this additional layer of processing of, wait, is that a face? Is that face oriented correctly? Are things weird? ends up being a more discriminable signal. So let me show you a video of the cursor control now. I would have shown this earlier, but they use inverted faces, and I didn't want it to be a hint, so I apologize if you had to imagine what it looked like. So it's a really, really fast protocol. What you're seeing in the, let me explain what's happening. So in the middle is going to be what your target is going to be for this round of trials. So in this case, it's pointing up and to the left. So this is going to be what you're looking for. So everyone focus on this, and this is what the subjects would do. So you're just going to fixate on that. All of the stimuli are going to be, flashed. And then at the very end, this is most likely sham feedback in the case of a training segment. But this is going to be the paradigm telling you, okay, this is the movement that we think you're thinking about or looking at, or that we've classified. But in a real speller, it would also just pick it'd pick the best one. So in this case, I think it's 100% accurate, which is why I think it's the calibration data set, because these spellers very infrequently are 100% accurate, or not even spellers, but cursor controls. But yeah, very, very fast stimuli, and the faces that are inverted are the best. So whoops, I definitely did not need to do that. Let's look at the next slide. So yeah, the way that we measure BCI performances tends to be in information transfer rate. This is the standard way that people will assess how quick your BCI was, and it's usually measured in bits per minute. You'll see BPM, but it's not beats per minute, it's bits per minute in this case. It's measured, the reason it's measured in bits, and if you're seeing all these log 2s, this is all based off of Shannon information theory. If you're in COGS 118C, you'll learn about this, or you've already learned about this. So it's just sort of an arbitrary way of having a standardized amount of units, right? Bits are a standard unit that don't necessarily, they're not exclusive to BCIs or anything. You could calculate the information that black holes take in and lose in bits and stuff. Don't quote me on that, but I think you can. But it's also not uncommon to see people talk about things in characters per minute, or more pragmatically, just actual words that people spell per minute. This is especially true if you're using BCIs that are probing for many entire words simultaneously or phrases. And part of this is because one of the things that is the most influential in the bits per minute calculation is the total number of potential targets that you have. So let's say you have a 100 by 100 grid of letters. If you're able to spell, with 70% accuracy in a 100 by 100, and you're also able to spell 70% accuracy in a 6 by 6 grid, you get way more bits per minute. Your information transfer rate is way higher in the 100 by 100 because it's a harder problem. There are way more potential stimuli to choose from. But that's not necessarily useful if you're just spelling one character, and it's kind of cheating if let's say your stimuli could be any top 400 word in the English language or something, then selecting a single word is not necessarily the same as selecting 1 in 400 if you're using language models and stuff. So it becomes more pragmatic in those cases to talk about your speller in terms of words per minute, just how quickly is somebody able to spell. And this is also a good way to compare it to typing. So I think that there's this data set that one of your TAs, Srini, is working on. It is an invasive MEA BCI where they actually use handwriting detection. And that, I think the spelling accuracy and speed on that is higher than people just typing, like regular bodied people typing. I'm pretty sure that's correct. Srini, if you're in Zoom, correct me on that. But I remember when I got sent that was what somebody put in the email, like, wow, this is faster than typing. I'm like, interesting. But that's atypical. Let me see what chat says. That's right? Okay, cool, yeah. So there is a BCI that's faster than the average person's typing speed. Maybe not your typing speeds. I imagine there are some pretty quick typers in here. But the average typing speed can be matched by an invasive keyword BCI. But it would be interesting to take some of those advancements and try to do it with non-invasive systems, for example. So the reason I brought that up is because this plot showing all of these different stimulus types are, we're getting the accuracy and we're getting the ITR, which is the information transfer rate. So in green here is the inverted faces. So the average accuracy was 88%, and the ITR was 38.7 bits per minute. And if we look for the highlighted icon, which was the worst, it's a 47% accuracy and only 9 bits per minute. And let's see what the upright face is, the one that most people chose. It's not even the second most accurate. So if we look, we can see that the upright eyeless face is better, and the inverted eyeless face is even better than that. So this is actually second place. And again, part of the reason why these are so good is because they're weird stimuli. It's not just that it's this thing that we're really good at processing and we see it every day. That's still good, right? The upright face is still good, and it's way better than the highlighted icon and better than the objects. But because there's this additional oddity, this additional unexpectedness, and it requires the brain to do additional work, we can get potentially more components, we can see more discriminable signals by using these nearly naturalistic stimuli, which is an interesting design. The thing to take away from this is how, if you're trying to design these new systems, what can we take about the knowledge we have for how our brain actually processes things, take the actual cognitive science, neuroscience approach to making these very much engineered systems more useful for the people that we're designing them for. And then this was the paper that was linked on Canvas. It's entered the novel protocols. They tried 5 different things, but I'm just going to explain briefly how these tasks work. I remember the first time I read this paper back in 2018. I think it was 2018. I was really confused about what they were actually doing and what they were testing. So I want to try to make it very clear. One sec. So you have this circle of circles, and you're going to be assigned a target. So an arrow is going to point, and it's going to assign you a target. And then once that's been assigned, it's going to de-illuminate, and then stimuli are going to be illuminated in a sequence. So in this case, maybe you get your target one first, maybe you get another one. This stays the same. The circles are always the same. The general elicitation of, okay, this is your target, look at this, and try to pay attention to when it flashes is the same. But they did a few different studies with this general paradigm. So one of the things is you'd have, just white stimuli that are going to be moving around randomly. So you can't predict which circle is going to occur next. And the goal of the task is to just count how many times your target is illuminated. So this is very much just a standard oddball task in this case. Look at your target. It's always going to be the same color. It's going to move randomly. Count every time your target is illuminated. They also did a variation where now your target could be, and any of the stimuli flashing could be either red or green. So your target might still be this top one, and it might be red or it might be green sometimes. But now, and they're still moving around randomly, but now your task can be 2 different things. Your task can either be count how many times your target is flashed, just like in the oddball paradigm, but then they did another experiment where it's like, okay, rather than counting how many times your target is illuminated, I want you to think of the color that you saw. So now it's not just, 1, 2, 3, it'd be red, and maybe sometimes it'd be green. So now it's a slightly different task, but still based off of the exact same thing, small set of modifications. And then the additional layer of modifications they made was that sometimes in some of the experiments, they're not flashing randomly, but the circles are actually moving in a clockwise orientation. So it'd be the top one, then this one, 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 this one. So that's called the periodic one. And again, you could have the periodic where you have just the the color and you count, or you can have the periodic where you say the color name, or you say it in your head, or it could just be the white circles. So this is the stimuli rotated either periodically or randomly. The colors were either random between red and green, or they were white, which is a standard oddball. And the task was either think of the color name or keep count of how many times you saw the target, which is just standard oddball. And this is how the protocols were named. So they have they have 5 different protocols, and this is their naming scheme that they used. It's a 3-part acronym. The first part is the type of sequence. It's either random or periodic, so it's going to be either R or P. Then you have the stimulus type. It's going to be either single color, SC, or random color, RC. They could have just used S and R. I don't know why they used the C. And then the third one is the task type, which is name or count, which is going to be N or C. And the reason why they needed acronyms was because in this paper where they're talking about all of these different protocols, it would be incredibly time-consuming to say and write out random single color name was better than periodic random color count, which is not true, but just as an example of a sentence. So these are all of the protocols that they have. So they have random single color count, random color count, random color name, and then periodic random color count and periodic random color name. And I don't know, did I include I don't know if I don't think I included the figures, but the one that was best was the periodic random color name. So again, if we think about this in context of this experiment, is you have your stimulus is going to be either red or green, and it's not going to be moving randomly. It's going to be moving, top one, then this 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 one. And your task is simply to, in your head, when you see your target illuminated, just think red or green. Super easy. It seems more confusing when you're looking at, all of these different protocol names. It sounds like, I don't know, this is some really fancy stuff. And the paper just reads kind of poorly because of all of these acronyms everywhere, but it really is just that simple. The best one is just say the color name in your head. The colors are going to be either red or green, and it's going to be moving in a predictable clockwise circle. That's it. And you could use that for cursor control, as you can imagine. So imagine that each of these is a direction that a cursor is going to be moving. And let's say that you are able to move your eyes and stuff. You can imagine a UI where these circles are actually surrounding a real cursor. So it doesn't have to be just like, you show this and then you flash a new screen where the stimulus is. You could have just regular mouse cursor, just like this, and surrounding it are a smaller version of these circles that are able to move it to the next step. Or you could have this be very similar to, you could take the hexospell design and have individual letters inside of, or individual characters or commands inside of these circles, and you could probe for it in that same way. So this would be an improvement on the hexospell, right? Because if we think back to the hexospell, all it's doing is it's highlighting a set of characters. It's not having you name the color or anything. It's essentially having you be like, okay, yes, my target was highlighted. So even this would be a simple modification that would theoretically improve the hexospell. And then if I had time, which I do, I was going to talk about the BCI speller that I've worked on, which is the segment speller. So let me, since we're talking about novel designs, might as well talk about the one I know the best. I'm going to skip through a bunch of slides because this was my second year project that I did in my first year. So the goal in this is sort of a spoiler of what the point was, but let me skip a million slides. As you can tell, I'm very fond of the black background, white text, and I used to not put any titles. Okay, so the goal was to create a spatially independent, parallelized hybrid speller. There's a lot of jargon. Spatially independent just means that you can have a system that probes for stimuli in the center of the screen. It doesn't require on information that's spatially distributed, so all of the stimuli are going to be roughly in the same place. Simple. Parallel, it just means that you're going to be probing for multiple stimuli at the same time. The row column speller, the original one by Farwell and Donchin, is an example of a parallel speller because you're probing for multiple letters at the same time by showing an entire row or an entire column. This design is a little different. And then the hybrid, this isn't something we've talked about a lot yet, but a hybrid BCI system is something that uses multiple control signals. So for example, in this case, I was using the P300, and I was also going to use the feedback negativity, which is another ERP component. But it doesn't even have to be EEG. A hybrid speller could use eye tracking and EEG, or heart rate and EEG, and EMG and EEG, or whatever. So hybrid is really just using multiple different control signals in order to create a more efficient spelling paradigm, which is almost always a good idea if you can use multiple schemes. So let me explain the psych speller with an analogy. This is Guess Who. Anybody here play Guess Who before? Some people. So I used to play this game with my sister all the time. For those that don't know, the main premise of the game is that you and your opponent are each selected one of these. You have one of these people at random, and you're trying to guess your opponent's person before they guess your person. And the way that you formulate guesses is by asking yes or no questions. So, maybe your question is, does your person have some sort of head covering? Try to get rid of people with head coverings and hats. So, does your person have head coverings? And then your opponent is going to answer yes or no. If they answer no, then you put down all of the people who have head coverings, and now you've reduced the sample set of people you have to choose from. The seg speller works in a very similar way. So we have this font where all of our letters are comprised of these segments. So the segments are always going to be the same, and the white dots don't mean anything. They're just kind of filler. And rather than asking something like, does your person have a head covering or not, we would ask, okay, does your letter have this segment in it? And we're going to flash people that segment. That's how we ask them. And their response is their EEG. So if we see a P300, then it probably is something that is in their letter, and if we don't, then it's probably something that's not in their letter. And once we're confident and we can determine that, okay, your letter doesn't have that segment in it, we can put down all of the ones that do have it and end up with something like this, the remaining letters. Now, this is an oversimplification because we don't get perfect classification accuracy, but we can't just say, okay, we didn't see a P300, therefore this segment is definitely not in your target letter. When you have accuracies around 70%, you have to be a little more strategic. So really I'm putting these things like 70% down, but it's not quite all of that. So what I do is I keep track of a probability distribution of all of the different letters. So I show somebody's segment, I'll record their EEG, I'll get the response. If I determine that, okay, this segment is not in the letter, I don't immediately say every letter that has this segment is definitely wrong. I just decrease the probability of them being correct, and I increase the probability of all of the other letters that don't have it being the correct choice. And we would iterate over this with many, many trials until one letter becomes the clear favorite. So in this case, we've whittled it down, and we think that the letter that the participant is thinking of is a T, at which point I show the participant an all-white version of the T, and I record the ERP from this. And this is not necessarily, okay, this might be a P300, but it's not going to be the P3B, we think. It's going to be something that I think is the reward positivity or the feedback negativity, which is where the hybridness comes in. So, the very last thing I'm trying to use a new stimulus for, and we choose this. This is roughly the seg speller. So the main innovation is you're probing for things in parallel in the same exact space, so rather than having to flash a row and column, which might make people look towards their stimulus or look away, participants are forced to look. There's only a single region of the screen that they can look at. They don't ever have to move their eyes around to look for different stimuli, which is something that people who are locked in or completely locked in can't do. So this was very much designed to be used by people who need it. It turns out not to be a particularly good system because of things that are beyond the scope of this class. Well, they're actually not beyond the scope of this class. Maybe I'll talk about them later. Anyway, this task ends up being uneven and a little bit too complicated for participants, but it's still an interesting novel design. But okay, that is all the time we have for today.